My name's Josh. I am going to be talking to you today about a folder, which might not sound that interesting, but I actually think it's really cool. If you haven't actually looked at procfs before, you might find some of the things here interesting. A lot of the abstractions we use, whether they be container runtimes and so on, oftentimes leverage, or at least their data that they are impacting surfaces at this level. So first, just a little bit about me. As Eric mentioned, I'm an engineer at Arctier, where the length of Arctier is 2. So it's a very small company. We're just building stuff right now. My background is mostly in Kubernetes. I worked at a company called CoreOS. They built something called etcd, which sits behind Cube. Then worked at Heptio for a while, and am now starting my own gig. I also am a co-author of a book called Production Kubernetes. If you Google free download of Production Kubernetes, there is a vendor who, for the exchange of your email address, will allow you to download all 500 pages for free. It actually was published 2 years ago today, or tomorrow, 2 years ago tomorrow. So yeah, it's a really cool book. It's a bunch of people who have been doing Kubernetes for a really long time, giving our perspectives about some of the different decision points. I'm going to start with a little bit around the concept of a process. And I know that many of you are probably like, oh my gosh, a process. We know what a process is. Of course we know what a process is, because a lot of us run commands like ps-aux, and we go in to our system and we see the SSH daemon, we see our shells, we see containerd, we see all of these processes. And at a high level, we know processes like this abstraction of a thread running an executable. More complex than that, but that's like a kind of a high level thing that we oftentimes consider. In fact, when we look at processes, we oftentimes use fancy, colorful tools like htop to see what's going on in our system. Sometimes we use top because we really love that monochrome vibe. And then again, as you just saw, sometimes we just use ps to kind of get some details about processes themselves. But what I want to talk to you about today is kind of how some of these process details surface such that we, using tools like this, can access that information, but also be able to go in and do some like deeper troubleshooting. The thing I love about procfs is I actually use it quite a bit when things don't make sense to me, especially with containers, especially with an app that's running 40,000 instances across a huge fleet of nodes and it's misbehaving in one instance. Those kind of really crazy things that I think can be quite helpful to troubleshoot. So if we just go back real quick to the slides, I thought I would hit you with just like a little bit of history of how procfs came about. So I'm going to take you back to 1984 at the Usenix Association Software Tools User Group, where the kind of first instance of procfs, to the best of my knowledge, came up in Unix version 8. The intent initially was, let's find a way to actually, I don't know if the intent was like to fully replace like ptrace, but to actually have like an interface, a virtual file system, or file system, if you will, where you could go in and see a file representation of processes running on your system. And since then, we have seen this kind of evolution come across a bunch of different operating systems, including but not limited to Plan 9. BSD had a really interesting progression where BSD was like, oh, let's do this thing. And then like they realized that this whole like reconciliation of a virtual file system of kernel level detail is actually like potentially security risks, potentially inefficient. It's a talk for a different day, but largely to say that unless you like mount it directly, a lot of iterations of BSD like FreeBSD and OpenBSD don't use proc by default. But we are here to talk about Linux because that's what most of us probably use for our Kubernetes clusters, our maybe serverless infrastructure, and so on. In Linux, since kernel version 0.97.3 has been using procfs to some degree, and it exposes a lot of details again about our processes that we kind of utilize. So let's like take a quick look before we dig any deeper on what's inside of proc. So you might have used proc quite a bit in the past. One of the really common things that you'll Google for is you'll say, how do I use the command line to tell me what my CPUs are on my Linux computer, right? And the really common way that people do that is that they say proc, they say CPU info. You can even see my history. I've done it in the past year. And then they get some information about their processor details. There's a similar analog to memory information as well, a bunch of cool stuff. But if we take a quicker look inside of proc itself, one of the themes that gets kind of picked up here are a bunch of folders with numbers associated with them, right? And you could probably infer what this is. These are effectively our process IDs on our running system. Okay, so let's talk a little bit about this idea of the proc PID directory, what's inside of it, what we can infer, so on and so forth. And let's go ahead and say that we're deep in a coding session. You know, we're digging into some arbitrary Go application in this case. So using a editor, be it VS Code, be it IntelliJ, be it whatever it is, you're probably using a language server behind the scene, which the language server gives you things like code completion and IntelliSense, I guess is the same thing, but you get the point about the code. And that is a process that is understanding the structure of your code and then providing insights on the basis of events that happen with your keyboard. So in this case, the Go project typically uses the Go Please LSP. So that's what you can kind of see here. And this is like a little process running in the back end, and my editor is kind of talking to it and being like, hey, I just typed a dot. What things might I complete with said dot? So we know that Go Please is running, or at least you can hopefully take my word for it that it's running. And if we do just a quick PS aux for Go Please, we can see that in the top here, 47727 represents Go Please itself. So what we can do is we can go into proc, we can go into 47727, and then there's going to be a set of directories that we'll dig into a couple of these today to kind of hopefully pique your interest about some of the interesting information that you will find inside of proc. Now, one of the coolest directories ever in proc is, of course, proc, and it is the stat directory with a bunch of different information about what's going on with this particular process. Now, a lot of this information might seem a little bit crazy, and that's because oftentimes we would use like a table like this to actually understand what is inside of our status file inside of proc. Tons of details in here. What's the parent process that's running the current process? What is the resident set size of the memory, which is like the actual memory allocated versus the virtual memory that's potentially allocated? A bunch of kind of interesting bits. Now at Arctier, the company that we are building out, we have a tool that we use, and it's open source and something that you can check out as well if this piques your interest. And that tool is called Proctor. So let's just run a quick Proctor command, and I'm going to just quickly switch this out from Nginx and call it Go Please, where we'll get some details on this. Great. And I'm just going to show you a JSON output here where we format the JSON. So let's do that. All right. And this is basically like a formatted view using our libraries where we actually like convert the hex values of the memory space and actually like, you know, put meaningful values in what was essentially in that status file, right? So we can see that this is Go Please. We can see that it has a parent ID. We can see a bunch of different details about what's going on with it. Now, the reason that this is cool is that the areas you can go with this and how nerdy you want to get with it are kind of up to you. So an example of a direction that you could take this is, let's look at the start env address of Go Please for a moment. Okay. So this is the start address for environment variables in the virtual memory space, where we could actually go into that and introspect the values that are available in this running process. So this is like crazy low level stuff. And we are going to use the GNU debugger to do it. So let's do, I'll do just a quick sudo command. And let me make sure I've got GDB installed. GDB, we'll get that. Great. Okay. And then I'm just going to do GDB. And let's remember 47727 here. So we'll attach to 47727 inside. Looks pretty good to me. And then if we scroll up, let's grab the start env address of this process that we're inside of. And we're going to do a GDB X. Don't worry about the syntax. You can chat GPT it because that's how we all figure these things out anyways. And we'll just put the memory address in here. And what I'm basically doing is I'm taking that start memory address that was available in procfs, and I'm actually looking through 10 of the contiguous memory addresses for environment variables that are linked to this process. So just by popping into that directory, I'm able to go in, I'm able to see memory addresses on the system. And obviously I could go into application memory here too. So you can imagine all the crazy stuff you could do. But this is at least exposing to me, hey, this process that's running, it knows what the environment variable shell means. It knows what xdg configures is, and so on and so forth. So there's really kind of this like low level understanding that we can gather that's largely exposed to us inside of procfs. Now, another really cool thing that I love looking at with procfs, and I'm going to again show you kind of the Proctor output here because I think it kind of cleans it up, is understanding the hierarchical relationship of a given process. So hopefully you've never had this headache before, but I have, wherein you're running a fleet of machines and you're running your web app, right? Let's call it like cool web app, right? Now, cool web app's running great in like 10 out of, or actually, let's make the number bigger, 100 out of 101 instances. But in 101 instances, there seems to be this weird behavior where there's like a different out of memory kill behavior happening or something weird like that. So you kind of go in and you're like, the binary, the process, it all seems the same. Like, what the heck is going on here? Well, using that proctor command and using again, the contents, you don't need proctor to do this. You can just go right into procfs. We can basically infer what the hierarchical relationship of the thing is. So let's do a tree, and we're going to do go please here. So we're just going to do 47727. We'll reset cache just because we are going to do that for funsies. And let's hit enter here. Proctor command tree. Oh, we got to do PS. I wrote this command line utility and I don't even know how it works. PS tree. And what we can see here, let's actually pipe this into Vim real quick, because otherwise it'll be really hairy to try to see. We'll do set no wrap. There we go. So now we can actually see the hierarchical relationship of go please on our given system. Now, the example that I was going with about like 100 instances out of 101 running consistently is that like perhaps, and this has happened, the init system at the lowest level here, system D, might actually be a different version on some other system because someone SSH into it. No one would ever SSH into a production host, right? But let's say hypothetically they did, and they like swapped out system D or something for some reason because they were testing something out and it never got cleaned up because we're not actually immutable, blah, 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 you know, architecture stuff all over the place, right? There's issues in our organization. It just naturally happens. Well, this hierarchical thing, we can actually understand how it's kind of passing up all the way to the go please level. System D has initted SSHD. I've come in through SSH into Fish. Fish has launched NeoVim. NeoVim has asked go please to launch. And then, you know, if you know much about like OS signals and kind of exiting things, you can imagine how like these signals can actually trickle up from kind of the parent and child relationship. Additionally, as I kind of scroll to the right here, in the case of Proctor, but this is really just like a SHA-256 call. In the case of Proctor, we can actually checksum all of the binaries themselves. So we can actually understand in that kind of chain sequence, like, hey, is there a difference between like the hashed value of all of these things in all these different systems? Like, imagine this for a moment. You've got all these SHA sums, right? And you just like fingerprint the SHA sum more or less, right? So then you could actually have like fingerprints that can uniquely tell you that a arbitrary, you know, n number of configuration parameters, be it binary SHAs, be it command line flags, be it environment variables, are all consistent across a fleet of machines. Again, just by producing a fingerprint, by taking this level of input data that once again is all entirely powered by our best pal here, the proc directory, right, with all of our different processes inside of it. Now, I'm going to talk about containers to kind of wrap us up here, but I figured like maybe I should just give you like a little visual, very complicated architecture diagram. If you're not familiar with what procfs is, it's basically the kernel's way of just exposing some details, both about the system and user space, which is a little bit contentious depending on which crowd you talk to. But regardless, it's what it does. It exposes it up in this folder that's usually mounted to proc, although you can move it around. Not sure why you would. Yeah, it just gives you a bunch of cool details. The reason that I'm like so stoked on this directory is basically because like a lot of our high level abstractions share, of course, low level abstractions, unless we're recreating the wheel every single time. So like if I am using Podman, or I am using Containerd purely, or Docker with Containerd, or like the 47 other container runtimes that are out there, like a lot of them are going to have their information kind of exposed through the same primitive. So if I need to debug a container issue, and again, I can't just do it from like a Docker PS level, which is probably where I'd start. I'm not saying go to this really low level, but I can actually go in and just kind of infer what's going on without having to really understand some of those higher level constraints. So let's talk a bit about containers and see how this kind of relates, because again, y'all probably know, because you've seen the picture of a VM versus a container like 47 times in your life now. You know that containers are like tricks with processes, right? Like we use these like kernel things like C groups, right? To basically go in. Let's see if I can cd into that directory again real quick. Actually, I'll just start a container and then we'll talk a bit about it. So C groups to actually allocate memory and namespaces, or sorry, memory and CPU, and then namespaces to actually slice off like networking capabilities and file system access and so on and so forth. So let's start Nginx, because that's the canonical example, right? So we're going to do docker run Nginx on this machine. And then let's see kind of how this relates to proc itself. So this is Nginx running. If I do a docker ps, you can see Nginx is running. Now that Nginx is running, let's go ahead and do a quick ps and look for all processes named Nginx. So here's a bunch of Nginx processes. Now these are all running in the container, right? Like when we do a ps, it doesn't say Nginx container, right? It effectively shows the processes that make up Nginx, because from the host level, these are, again, effectively just processes. And what's interesting about this is there's just some like properties around them that are effectively isolating them and doing different kinds of things. So like, let's go into what I probably could presume is the root process, which is this Nginx master process daemon off thingy. So we'll go ahead and copy this, and I'll just go into sudo real quick. Let's go back here. So we'll go to sudo and sudo I. All right, so we'll go to proc, and we will paste this number in without a space. So we'll get that. Great. All right, so now we're inside of what I perceive to be Nginx. One of the cool directories inside of proc is the exe directory. So if we just do actually an lsla of exe, it will show the Nginx binary that's being run. Now, this is, again, in a container. So what's interesting about this environment, and I just happen to know this because I know my host, this is not a path that exists on my host. I can guarantee you that, especially being like a Nix OS environment, nothing works this way. If I go to user sbin Nginx on this computer, no way, Jose, it's not going to happen, right? So what is actually kind of going on here? Well, first thing we can do is we can kind of understand some details about the container itself. So let's go ahead in the proc directory, let's cat the cgroup directory. So what we can actually see here is that in systemd, the init system, Docker, and the pieces underneath Docker, but I'm gonna say Docker at a high level, okay, has talked to the init system, been like, hey, let's slice Docker out of this thing, and let's put Docker in this really specific arbitrary slice. So another really common tool we could use to kind of go forward is we could say, okay, sweet, so I know it's in a slice. Let's do systemd cgroup ls. And this will give us a full output of all the different slices, because slices themselves are hierarchical in a Linux system. So inside of system is Docker. Inside of that is the Nginx instance. So if we just search quickly for Nginx inside of here, we could actually see the slice itself and the processes. Notice there are multiple PIDs here. So if we went and catted that C group inside of the different proc directories for every sub worker process, we would actually see that they are sharing this C group. So again, kind of a deep level of introspection and understanding we can gain. And we could even take this a step further. This is something that I kind of love to use a lot when stuff gets real weird, is let's go ahead and start and run. So we'll run Nginx. Okay. Docker run Nginx. And then let's see if I remember this command actually. Is it memory 512 megabytes? I can't remember the flag. Okay, anyways, let's just pretend I put the memory in there for whatever Docker's command is. What we can essentially do is we can say systemctl show, and then we can ask for, let's go back to our cgls current working directory. Where am I in? Oh, I killed Nginx. That's why. Here, let's start Nginx one more time. Cool. All right, so we've got that psaux Nginx. Great. So we are going to go into proc, and we're going to go into this time 49399, right? We'll go there. We're going to cat the C group file again, and let's go ahead and take this little C group scope. So we'll grab that, and we're going to say systemctl show, and let's paste this in. And this is going to give us all the details about this, how the C group is configured. So again, like, I don't know how containerd might do something versus how Docker might do something, although they're using each other, right? Versus Podman versus whatever. But I can actually go in here and understand some of the parameters that were set on the C group level of that given container. For example, the memory available infinity, that's that flag I was trying to remember. Who knows what the heck it is, right? I mean, I'm sure many of you do, but I don't know offhand. But if I had set that memory flag specifying that Nginx can only use 512 megabytes of memory, I will see a memory value in here in bytes that looks quite similar to that. So just like at the system level, I'm going in and I'm saying, hey, show me some details about how this thing is configured from that systemd slice level. So memory, it'll tell you your CPU allocations and so on. All of that is available in here, and again, all of it can be inferred by looking up this C group file that happens to be inside of procfs. So pretty cool. There's something I kind of glazed over, maybe like a final example I'll talk about here is that sbin thing, the sbin nginx, it wasn't there. Do you remember that? So if we do ls/la and then we go to exe, we need to be sudo Josh. There we go. User sbin nginx. It doesn't exist. Now, why doesn't it exist? Well, in the case of Docker, at least in like a default configuration, containers use an overlay file system. Typically, you find this inside of, oh gosh, I hope I remember this directory, varlib Docker over, yeah, nice. I haven't used Docker directly in a while. Overlay 2. So these are basically a bunch of the kind of file system directories that a lot of stuff happens to make the container kind of understand the merged output of this file system is like a standard Linux file system. Or yeah, I guess you'd call it a standard Linux file system, sort of, kind of. Not because obviously it can have like no directories in it essentially, but you get the point. It's a file system nonetheless, and it goes through this thing called a overlay file system. All right, so we're back in Nginx. One of the kind of cool things that we can do to understand some of the mounts and how this kind of overlay file system works is we can actually cat the mount info file, another great file in this lovely directory. So inside of mount info, there's a bunch of information here about a bunch of things. Like this is a lot of system-wide information, to be clear. But what you will see is I can actually see this kind of root mount location, and I can kind of dig in and be like, oh, okay, so this is the Docker overlay 2 mount. Docker has a couple things that are maybe, or container images in general perhaps have a couple things when using overlay that are really specific. Like they have something they refer to as a lower dir and an upper dir. And a work dir and a merge dir. I'll leave it as an exercise to you to chat GPT the meaning of those things. But putting all of that aside for a moment, I'm just going to skip ahead and say this work dir is definitely significant. So Docker overlay 2, and then some ID for the overlay. Note this is not the container ID, okay? Because containers have multiple layers. This is just an arbitrary layer that represents kind of this this work directory for the process, okay? So what we're going to do is we're going to go back into sudo here, back into root, if you will, and we're going to cd into that directory. So let's go in here. Now I'm in this very long file, and inside of here there are some other directories. Again, exercise to you if you're interested enough to learn what these are. But I'm going to go into the merge directory here, and now if I ls/la, what does this look like? Well, this looks to me like a Linux file system. I'm guessing it looks that way to you as well. Obviously, there's some hints here, like that Docker env thing that they throw in there. There's some interesting stuff about the entry point and so on. But the question I'd have for myself is like, I wonder if that Nginx binary that's supposedly sitting around is actually in here, right? So let's see. So if I do ls and I do, what was it again? Was it user sbin? There it is, right? And then using our tools on the machine, because note that I'm not like ns entered into the namespace. So ns enter is another command line utility that you can like enter and mount into the file system of the container. I'm just like introspecting the layer files that Docker is persisting onto the host. So, an example would be like, I could go in and like SHA-256 sum the actual Nginx binary in the actual container, right? Would you ever need to go this low of level? Probably not, but it's just cool to know you can do it. So we do a SHA-256. It's actually taking, again, the Nginx binary that, last time I'll say it, sorry, lives in the container, right? Not necessarily on the host, but actually in the container itself. So yeah, I mean, basically you have this ability to dig in inside of proc and explore tons and tons of directories that kind of show the different relationships behind how different things work. And I'm not going to try to like sell you on going into proc constantly. Many of you probably hold the philosophy of like, I should never have SSH access or worry about this level of detail. And I completely agree. But like, it's really fun. Like, we work on computers. Computers are really cool. And it's just really neat to kind of like understand a couple layers down how things expose themselves. And, I'd even argue, if you like ever want to dig into proc and kind of learn a bit more about some of the stuff in this table, that it kind of teaches you a little bit about how the kernel works. Like, there's some history in these values, by the way. There's some that we don't use anymore. There's these things called jitter measurements for sizes. What are those, right? Like, so much really neat stuff to kind of learn about. And if you're a bit of like a programming history buff like me, you might just kind of enjoy, reading the mailing list where they talked about adding or removing or deprecating, things from here. So it's a really, really kind of cool thing that we can take out. And this is truly just scratching the surface, right? There are so many more details inside of proc that we can learn about. And there's a bunch of other folders like the sys folder, for example, that has other information as well. If you leave with anything today, possibly you're just going to leave with a little bit of useless knowledge that you might not use day to day, but hopefully it's kind of piqued your interest. If you haven't explored some of these lower level pieces, hop onto one of your hosts in your development environment, poke around, see if you can get the environment variables. Like the environment variable thing where I used the GNU debugger was like insane overkill, right? Because although that is like I guess the most true way to see what is in memory, but what I could have also done in proc is I could have just asked for the environ file, if I sudo it, of course, and this would give me any environment stuff available to that as well. So like many different ways to approach some problems, but just kind of a cool, really low level way to more or less understand what's going on.